Hey everyone, welcome to the review videos for the final exam. So we're going to start in Chapter 1, and kind of the only new stuff we encountered in Chapter 1 were in Sections 5 and 6, so we're going to focus on that. Section 5 is all about limits. And let's recall what a limit means. We write it in this notation, and when we see the limit as x approaches c of f of x equals k, what that means is that as the x values get close to c, as the x values squeeze into c, the y values, or the f of x values, squeeze in close to k. So here I've drawn a function where as the x values get close to c, the y values also get close to k. Even though f of c is technically undefined, as we can see by this kind of open circle here. So the function isn't actually defined at f of c. But as the x values get closer to c, the y values get closer to this k. Okay, so that's what it means to be a limit. We get close in the x direction, we limit to something in the y direction. Most of the section about limits is all about computing limits. And usually the good news is that you can just plug in. So for example, let's say we want to compute these two limits. All right, so over here on the left, we have the limit as x approaches 4 of 3x squared plus 11x minus 1. And we can find this by just plugging in 3 times 4 squared plus 11 times 4 minus 1. This is 48 plus 44 minus 1, which works out to be something. I think 101? Yeah. And ta-da, we did our limit. And here on the right, again, we can just plug in. In general, you can just plug in unless something breaks. But here, if we try plugging in, we get 2 squared plus 11 over 2 plus 3. This is 15 over 5, which is 3. And so our limit is 3. And so if we look at the graphs of these, as x approaches 2 over here, we would get y values approaching 3. The unfortunate news is that sometimes you can't just plug in. Let's take a look at this guy here. We want to determine the limit as x approaches 3 of x squared minus 9 over x minus 3. If we try plugging in, so if we try the good old plug and chug, we're going to get 3 squared minus 9 over 3 minus 3. That's 0 over 0. And if we ever get, divide by 0, we did something wrong. The good news is there are 3 things we can try to solve this. The first is the table method. The table method is, well, if we want to know what happens as x approaches 3, we can make a table of x values and f of x values, and we can pick numbers getting increasingly close to 3. So we can start with, say, 2.5, 2.9, 2.99, 2.999, 3, we don't know what's going to happen there, 3.0001, 3.001, and 3.01. And then, let me actually draw this table out, and then we can plug these into our favorite calculator. So let me actually bring up a calculator here. Here's one. Not quite the one I was looking for. Perfect. And let's say that f of x equals x squared minus 9. That whole thing divided by, divided by x minus 3. So that's our function. And we're going to plug in increasingly close x values. So 2.9, f of 2.99, f of 2.999, f of 3 is undefined, of course, f of 3.0001, f of 3.001, and f of 3.01. So we've got some values really close to 3, both less than 3 over here and bigger than 3 over here. Let me plug these into my table before I switch back. So we have these in our table here. And it's clear that, hopefully it's clear, as we plug in values that are closer and closer to 3, our output values are getting really close to 6. So f of x gets close to 6. So the limit as x approaches 3 of x squared minus 9 over x minus 3 equals 6. That's the table method. It's very crude and unrefined, but it works. A better solution, possibly better, is the method of algebraic simplification. So what do I mean by algebraic simplification? I mean, we can take this thing here, we can rewrite it, get some cancellation on top and bottom, and then take the limit by just plugging in. So x squared minus 9 over x minus 3, well, this is the same as, we can break apart the top. X squared minus 9, that's a difference of squares. So this becomes x plus 3 times x minus 3 all over x minus 3. And difference of squares, let me make a little aside here. If we have like an a squared minus b squared, that's the same as a plus b times a minus b. All right, that's just a thing you need to know. If you have a limit question, this might come into play. So that's how we got this simplification up here. But from here, we can cancel out. We can cancel out the x minus 3 on top and the x minus 3 on bottom. Let me change colors back to what I'm working with. And so this gives us that the limit as x approaches 3 of x squared minus 9 over x minus 3 is the same as the limit as x approaches 3 of x plus 3. And that one we can clearly plug in because we don't break anything. We get 3 plus 3, which is 6. Okay, so that's algebraic simplification. The other rule, and this one I kind of briefly mentioned in class, but I think it's worth repeating here. The other thing we can use is something called L'Hopital's rule. And L'Hopital's rule says if we have something where we have, kind of in this situation here, if plugging in gets us 0 over 0. So L'Hopital's rule says if plugging in gets us 0 over 0, then the limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of x over g prime of x. So here, we plug in, we get 0 over 0. So if you want to find the limit of x squared minus 9 divided by x minus 3, we can take the derivative of the top and take the derivative of the bottom. So the limit as x approaches 3 of x squared minus 9 over x minus 3 equals the limit as x approaches 3 of, and then the derivative of the top is 2x, the derivative of the bottom is 1, and now we can just plug in. So this is 2 times 3 equals 6. This is probably the most elegant way to find limits. All right, so let's take a look at another example where plugging in doesn't work. We want to find the limit as x approaches 3 again of the square root of x plus 1 minus 2 all divided by x minus 3. So if we try plug in, we get the square root of 3 plus 1 minus 2 over 3 minus 3. This is 4, so the square root of 4 is 2. So this gives us 2 minus 2 over 3 minus 3, which is 0 over 0. And there are the multiple ways we can go about it. I'm going to ignore the table method. I'm going to look solely at algebraic and L'Hopital's rule. To solve this algebraically, we need to employ something called multiplying by the conjugate. Multiplying by the conjugate just means the complicated part that has a square root in it. What we're going to do is we're going to take this entire top section and we're going to multiply by the square root of x plus 1 plus 2. And of course, if you do something to the top, in order to maintain equality, you must multiply the same thing on the bottom. Okay, why are we doing this? Well, it's kind of like the difference in squares in reverse. So if we have a squared minus b squared equals a plus b times a minus b, we're starting out over here with a minus b, and we're multiplying by an a plus b to get this thing here. And it's nice, it's going to give us some good cancellation. Let me change colors back here. After we do this multiplication out, we're going to get x plus 1 minus 4 over x minus 3 times the square root of x plus 1 plus 2. So this is x minus 3 over x minus 3 times square root of x plus 1 plus 2. Oh, and technically I should be writing limit as x goes to 3 here, because that's what we're trying to compute, is the limit as x goes to 3. But now we have cancellation. The x minus 3 on top and bottom cancel out. So this equals the limit as x approaches 3 of 1 over square root of x plus 1 plus 2. Let me rewrite that to make that prettier. Now we can plug in, and we're going to get 1 over 4. Sorry, couldn't calculate the square root of 4 again. We're going to get 1 over 4. Now, we can also use L'Hopital's rule here. Because again, when we tried plugging in, we got 0 over 0. L'Hopital's rule tells us that the limit as x approaches 3 of square root of x plus 1 minus 2 over x minus 3 is the same as the limit as x approaches 3 of, and now we need to take the derivative of the top and the derivative of the bottom. To find the derivative of the top here, it's helpful to write this as x plus 1 to the 1/2 power, and we have to use our chain rule. We get 1/2 times x plus 1 to the minus 1/2 times 1, and then the 2 goes away, and then the bottom we just get 1. So this is the same as the limit as x approaches 3 of 1 over 2 times x plus 1 to the minus 1/2. And I get this just because since we're dividing by 1, we can essentially ignore it. So I'm just rewriting the top here. And this is the limit as x goes to 3 of 1 over 2 times x plus 1 to the 1/2. And if we plug in 3 here, we're going to get 1 over 2 times 4 to the 1/2, which is 1/4. So that's multiplying by the conjugate in L'Hopital's rule. And with those, you can pretty much solve every limit that you need to. That being said, there is one other time where plugging and chugging is insufficient. And this is when we're dealing with piecewise functions. So here we have a function that is piecewise defined, so it follows different rules if we're on different pieces of the number line. We want to find the limit as x goes to 1 of f of x, where f of x is given by 2x plus 1 if x is less than or equal to 1, x squared minus 1 if if x is between 1 and 3, and 4x minus 4 if x is bigger than 3. If we try plugging, we have that f of 1 equals 2 times 1 plus 1. And that's because 1 is certainly less than or equal to 1, and so we follow this rule here. And this gives us 3. But this isn't quite sufficient, because in order to know a limit, we have to know the limit as x approaches 1 from the left, and we have to know the limit as x approaches 1 from the right. So when it comes to piecewise functions, it's often really helpful to break this limit apart into two limits. So let's compute the limit as x approaches 1 from the left of f of x. So here we're looking solely at numbers that are less than 1. So think 0.9, 0.99. Well, if we're less than 1, then f of x is going to follow this rule here. And this is clearly something we can plug into, because if we're dealing with a polynomial, we can always just plug in. And as we saw before, this is going to give us 3. So the limit as x approaches 1 from the left of our function is 3. But what about if we approach 1 from the right? So if we're plugging in numbers bigger than 1, think 1.001, 1.002. Well, if we're bigger than 1, then we follow this rule here, because we're bigger than 1. So from the right, the limit of f of x is going to be the same as the limit as x approaches 1 of x squared minus 1. And again, this is a polynomial, so we can plug in. We're going to get 0. So the left-hand limit and the right-hand limit don't agree. So the limit does not exist. Even though we plugged in and got a value, the limit doesn't actually exist. The moral of the story is when dealing with piecewise functions, I can't spell, piecewise, it's helpful to break apart. And consider left-hand and right-handed limits. Or I'll write it limits from left and limits from right. So that's limits. The next and kind of last section in chapter 1 deals with continuity. So a function, f of x, is continuous at x equals c if we have 3 things. 1, f of c has to exist. If the function isn't defined there, it's not going to be continuous. 2, the limit as x approaches c has to exist. And 3, the limit and the function have to agree. If f is continuous at every point on an interval ab, we say that f is continuous on ab. And if it's continuous on all the real number line, we say it's just continuous. So some fun facts. Polynomials are continuous. Oh, let me move my mouse pointer off the screen. Polynomials are continuous. So something like this, 17 times x to the 100 minus 23x cubed plus x minus 1. It's really hard to compute, but we know it's continuous because it's a polynomial. And 2, rational functions are continuous, where the denominator isn't 0. So let's think back to this rational function we just found the limit of. This thing is going to be continuous as long as we're not at 3, where the denominator is 0. There are 3 types of discontinuities. We have a jump discontinuity if the left-hand limit and the right-hand limit don't agree. So if we look back at this function here, if we were to actually graph it out, the function would jump from one value to another. And it's called a jump discontinuity because if we graph it, the function looks something like this. There's a jump. We have a discontinuity at infinity if the limit as x approaches c of f of x equals infinity. So something like this would be a discontinuity at infinity, where as we get closer to x equals c, the function just blows up really large, or alternatively blows down really small, blows up really small. Or I guess it could be like this, where one side goes up to infinity and one side goes down to infinity. But if infinity is involved, we have a limit, we have a discontinuity at infinity. And then the third type of discontinuity we'd see is a removable discontinuity. And this is places where the function and the limit don't agree, or f of c doesn't exist. And they're called removable because it looks like you removed a point from the function. So it either looks like this, or it might look like this, where the function is defined there, but the function and the limit don't agree. Or if the function is undefined, it looks a little something like this, where the function isn't defined, but the limit does exist. It's called removable because it looks like you just removed a point. I think one kind of question that kind of encapsulates all of continuity in and of itself is something like this. We want to find what values of a and b make f continuous. So I've actually plotted a little something here in Desmos where we have this function. It's the same as the one I had written down earlier, and we have sliders for a and b. So if we move a around, this little section in the middle moves around as well. And if we move b around, this little section in the middle moves b around. Our goal is to make this part of the function, like this part of this middle line here, the very left end, match up to the very right end of this part here. And we want to make the right part of this part in the middle match up with the left part of this thing here. Okay, so we want to find the values of a and b where if we twiddle with this enough, we can get this line to bridge the gap between this line and this line. I realize I'm saying this and not necessarily gesturing, so I apologize if that's a little confusing. But how do we do this? Well, thinking back to the lines that we had, what we want is we want ax plus b to equal -1 at x equals 3. And we also want ax plus b to equal 4 at x equals 7. So I have x equals 3 here because it's the right endpoint of this part of the function. It's the left endpoint of this part of the function. And I have 7 here because it's the right endpoint of this part of the function and the left endpoint of this part of the function. All right, so 3 and 7 are the places where one part of the function ends and another part begins. And we need those two parts to equal each other. So let's go ahead and solve these. ax plus b equals -1 at x equals 3. That means that 3a plus b equals -1. And if ax plus b equals 4 at x equals 7, well, that means that 7a plus b equals 4. Okay, that was weird. My recording failed, but here we are again. We want ax plus b equals -1 at x equals 3. So this tells us that 3a plus b equals -1. And we want ax plus b equals 4 at x equals 7. So this gives us that 7a plus b equals 4. So this top line here, we can rewrite this to give us b equals -1 minus 3a. And so then we plug that into here for b, and we get 7a plus -1 minus 3a equals 4. And so we have 7a minus 1 minus 3a equals 4, which is 4a minus 1 equals 4, 4a equals 5, and thus a equals 5 over 4, which is 1.25. And if we plug that into this line here, we have that b equals -1 minus 3 times 5 over 4. So then b equals -1 minus 15 over 4. So then b equals -19 over 4, which this works out to be about -4.75. And sure enough, if we go into Desmos over here and we change a to be 1.25, it needs to be like that, and we change b to be -4.75, look at that. Sure enough, we've bridged the gap and we have ourselves a continuous function. And that is it for Chapter 1. I'll see y'all in the Chapter 2 review.